this simple one right here because it's visual. So let's go now to Bayes' rule. Okay. I'll say, whoops, slide down to my red line. Bayes' rule. Let's let A1 to something be a partition where the probabilities of the AIs are known, and let B be an event where the conditional probabilities, probability of B given AI are known. Okay, so that's the layout. As I said, a Bayes' rule problem switches this conditionality right in here. Okay, so let's pick some AK. So I've got a specific one. Okay, so this AK is one of these partition pieces. Okay, it's what's the probability of AK given event B. Okay. This only takes us about 2 minutes to write this all out using our regular conditional probabilities equation right from the start. That's going to be the probability of the intersection between that particular AK and B over the probability of B. Okay. And then we started out this conversation saying that this numerator could be expressed as a conditional probability either by conditioning on the AK as was given us in the problem or by conditioning on B, right? So what we can do right now is switch this back to the form like this. And that numerator becomes the probability of AK times the probability of B given AK, right? And you'll know you're on the right track if you see the conditionality has changed between the way the problem was originally phrased and the equation you're landing on. And that's really about it, okay? The only thing, almost every book takes this probability of B and writes it as the law of total probability right there, right? And so then you get a sum, I goes from 1 to whatever, okay? Probability of the AIs times the probability of B given AI, okay? And that's known as Bayes' rule.
Which is not the same as the Bayes' rule we wrote down before? Is this the second?
The rule we wrote down before is called the law of total probability and is this denominator, right? So for instance, in that last problem, right, which we've half done because we found the probability of a defect. So okay, do you want to write that? Are you leaving that? I can fold this page in half if that helps. So back to the supplier's example. Right? Given a part is defective, what's the probability it came from supplier C? And we do know a few things already, and so we can save ourselves. See, we've already done this. This right here is going to be that denominator, right? Right?
Because that's the given.
Because that's the, yeah, as we've switched this around. So the question now becomes, given a part is defective, what's the probability that it came from supplier C, right? As fancy as Bayes' rule is, I find myself always just starting from scratch and using conditional probabilities. You know, that's the probability of C and D over the probability of D. But now I'll use that switch in condition of ways to express this, right, which is the essence of Bayes' rule. That numerator can get rewritten as the probability of C times the probability it's defective if it came from C over the probability of D. And then if we go back to our original problem, let's write what we know here. Probability of a defective part from before the break was 0.021, right? We also had in here that, the probability of C was 0.1, 10% of the stock was purchased from C. Of the stock we purchased from C, 8% was defective. How's that look? How's that look? So what have I got? 0.008 divided by 0.021. Okay, whoops. 0.008 divided by 0.021, try that again, is 0.381. Okay. i.e. 38.1% of the defective parts we have, came from supplier C. How does that look? Does that look okay for us, please?
So with the process, we want to find the probability that it came from C given that it's defective.
Yes.
We can rewrite that using the conditional probability law we've been using this time.
Yep.
And then we can rewrite that using Bayes' law,
Right
which
in here.
allows us to basically swap around the information,
Yep.
unravel it, and use givens that we already have.
Exactly right.
Okay.
Exactly right. How's that feel? Well, let's see, 15 minutes. We got enough time. Let's do one more example. Let's see. There's that. I'll put that there. Okay. This example is, if you haven't seen it, you have to see it once. It's one of those classic examples that everyone, who takes a course like this should see. Okay, and let's see. Give this a go. Suppose. Let's talk about testing for a disease. Okay? Suppose that one in 1,000 people have a particular disease. And this what we're about to see is most pronounced for these rare events like this. I don't know if 1 in 1,000 would be considered rare events. But so the probability of having the disease is, what is that, about a 0.001? Does that look right for us? Right? That's called the prevalence of the disease. This is called the prevalence. You know, thinking back to the early days of COVID, this was really quite a mystery because some people had symptoms, some people didn't have symptoms, some people didn't test, some people didn't report, you know. So this was a big nebulous thing back in those days. There was really just no idea how prevalent it was.
So I have just a working with it question. Do you have any tips? Because we have now moved, it's 1 in 1,000 people. So our big, no, it's 1,000.
On average.
But 1,000 is our 100. 1,000 is our 1, right? Because that's the total.
You can think of right.
Okay.
So then if a random person is selected, what's the probability they don't have the disease?
99.99%.
I think you might have a couple extra nines there if it's 1 in 1,000, right? 0.999, right? And so, right?
Yeah.
0.1% have the disease. Should do examples with words I know how to spell. Disease. And 99.9% do not. Right? So the probability of not having the disease is 0.999. Okay? And there's a test for this disease. Okay? There is a test for this disease. Okay? But, you know, like all things, it's not perfect, right? But it's not perfect. If a person has the disease, the test is positive, with probability 0.99. Okay? So the probability that they have the disease, the probability if they have the disease that the test is positive, I'll use a plus sign for positive, is 0.99. Okay? That's called the sensitivity of the test. Furthermore, if a person does not have the disease, the test result is negative 95% of the time with probability 0.95. Okay? So in other words, given somebody does not have the disease, the test is negative with probability 0.95. That's called the specificity of the test. And by the way, oftentimes, you know, if you think about it, a lot of times you'll see that that by design the sensitivity would be higher than the specificity. Yeah.
What's the difference between the sensitivity and the specificity? Is it the negative?
One is correct positives and the other is correct negatives.
Okay, cool.
Yeah. And by the way, if you think about it, why would they probably try to maximize the probability on the sensitivity, right? Kind of comes down to this. Where are you most at risk? Telling a sick person they're healthy or telling a healthy person they're sick?
Sick person or healthy?
You know? And so if I were the physician, kind of like if you watch the Channel 8 weather, they always report the weather a little harsher than it's really going to be, right? Because they want people to be over-prepared, not under-prepared I'd rather err on the side of telling somebody, you know, you might have this disease, be careful, rather than telling somebody who does have the disease that you're fine, go on with things as normal. You know what I mean? There's a balance there, okay? So, question is, somebody just took the test. They got a positive test result. What's the probability they have the disease? Person just got a positive test result. Okay?
So it's the probability they have the disease given they have a positive test result.
Yes, and you hear that conditionality change that makes this a base rule problem. Yes. What's the probability they have this disease? Right? And so there we go. Okay, you can call this the false positive paradox or whatever you might want to. And by the way, this kind of is a nice example because remember you were asking if a partition could consist of just two groups. It's doing precisely that in this problem where we've partitioned our population into the healthy and the not healthy people, right? And so, in the spirit of time here, the probability of having the disease given you got a positive test result, right? And I know we talk about it in terms of Bayes rule equations, but I'll still, I'm still an old school conditional probabilities work just fine. Probability of having the disease and getting a positive test result over the probability of having a positive test result. Right? Now, that I'll add one more step here, right? That numerator is the probability of having the disease and a positive test result, right? That denominator, that event getting a positive test result, well, that's a compound statement if you start thinking about it, because there are two different ways a person could get a positive test result. A test result because they've got the disease, or a test result and they don't have the disease, right? There's that partition, the law of total probability, right? So we'll take that and we'll split that into the probability of having the disease and a positive test result, or not having the disease and getting a positive test result. Let's put these together into more of a Bayes rule form. That numerator, we can change that conditionality like you suggested. It's the probability of having the disease times the probability of testing positive if you have the disease. Okay, good. That gets copied in that first one down here, so I'll put that there. The probability of having the disease times the probability of testing positive if you have the disease, right? The other option is you don't have the disease, but you got a false positive, right? The probability of not having the disease times the probability of a positive test given you don't have the disease. Right? Okay. All of these come off our givens pretty straightforward, except for maybe one piece. Okay.
Which is the positive test, even if it's a false positive?
That's right. And so let's look at that for a second, okay? Now the numerator, okay, only 0.1% have the disease. Amongst that pool, the test is pretty accurate 99% of the time, right? Plus, okay, like you said, the vast majority of people don't have the disease. In fact, 99.9% as a proportion, 0.999, okay? And now this one thing that I didn't quite address earlier here, okay? but we've seen this in action, right? With the specificity of the test, the probability, given a person does not have the disease, the test is negative with probability 0.95. So based on that, if a person does not have the disease, what's the probability that they'll get a positive test?
0.05?
0.05, right? Don't forget, those are gonna be those branches in that tree there, right? And, or 1.1 minus 0.95, but 0.05. Okay, this is the probability of a positive test result given you don't have the disease. There you go, there you go. Let's look at this and see what it says. Buckle your seatbelts for a second. 1 times 0.99 divided by 0.001 times 0.99. Is anyone checking my work as we go?
I'm trying to, but I don't necessarily trust the calculator on my phone.
Does anybody get something?
.019.
019.
Yeah,
That's what I got too. That's what I got too. So, okay. All your seatbelts are buckled, I can see, right? So given somebody gets a test result, there's less than a 2% chance they actually have the disease.
You mean they don't have the disease if they get a positive test result?
I'm saying if they get a positive test result, there's a less than a 2% chance they actually have the disease.
It doesn't make sense.
That's why I started out saying this was kind of a conundrum or a paradox, right? Right? And so, with a positive test result, there is a less than 2% chance of actually having the disease.
So I never had COVID all the time.
I agree with all those numbers in there, and it does cause a little bit of a puzzle, right? But if you think about it now, our time is up. We can digest this a little bit. Oh, we're not going to meet till Monday, but here's the issue. The issue is that this is a very rare event. Only 1 in 1,000, right? And so, if I think about all the people in here, there's all my whole population, right? How big a space should I build in there for those who have the disease?
Because it still makes sense because so few people have the
Right?
disease.
Do you see what I'm saying? That is my 0.1% of my population. So in other words, the 5% of the huge group is dwarfing the 99% of the little group. That's what's happening there. Do you see that?
So I guess if you get really deep into the numbers, it becomes paradoxic. But if you just look at the fact that you were overwhelmingly more likely to not have it
Then
have it.
that's the weight. That's what's driving things. That's why you hear things like, if you test positive, don't believe it, but get tested again. Right? Other ways to try to mitigate that, and that's a fact of life for any kind of testing of any kind of unusual thing like that. Anyway, oh, you let me go over. Okay, good. Well, Bayes rule.
That was so cool. Thank you so much.
That was fun. All right.